Let's consider the bond between two atoms more closely. Here, for example, is an ionic bond as it exists in sodium chloride and cooking salt. In the force-distance diagram, the attracting component is defined as negative and the repelling component as positive. A status of equilibrium exists at zero energy. Imagine an ion is at the origin of the coordinate system. A second ion approaches the first one from the infinite distance. The force of attraction is proportional to 1/r. The closer the chlorine ion comes to the sodium ion, the greater is the force of attraction. However, the force of repulsion also increases with increased proximity. It is assumed to be proportional to 1/r raised to 12 here. At very small distances, the force of repulsion is significantly greater than the force of attraction. The sum of both curves show the energy progression on the bond. Status of equilibrium exists at the minimum of the curve. Thus, it defines a bond distance. The depth of the potential trough, that is, the absolute value of the minimum of the energy curve, provides information about the bond energy. The deeper the potential trough, the higher the thermal and chemical stability of the bond. Materials with ionic and covalent bonds typically have deeper potential troughs than materials with metallic bonds. The first derivation of the resulting energy curve, according to the path, corresponds to the force effective on the bond partner. It has a null or a 0 point at the minimum of the energy curve. This means the resulting force on the bond partner is equal to 0 in the state of equilibrium. The energy curve has a maximum at the point of inflection. This corresponds to the strength of the bond.